My name is Sam Nodal. I've been with Leap for nearly 19 years. I've been doing different things like training, support, sales, and consulting. So I've got a master's in a master's degree, and I've also done a mechanical engineering degree. All right, so today's topics are advanced contact and material non-linearities. So the idea is I go through these slides and then maybe do one or two examples to demonstrate some of the concepts, and then I'll move on to the next section and do the same thing. All right, so I think Hashan covered some basic contact. So some of the stuff you'll see here might overlap. So I apologise for that, but it's just to sort of tie everything together. I need to cover the other stuff. All right, so we'll look at the differences in contact types, contact results, frictional contact. We'll talk a little bit about contact formulations. We'll spend a bit of time talking about contact stiffness, and also how we deal with interference and gaps in contact, which you will sometimes encounter. Okay, so what is contact? So in practice, you'll more often than not have multiple parts in an assembly that you're analysing. So those parts will have certain mating relationships that you may have created in CAD. They're not taken into account in the simulation. So we have to introduce contact to be able to deal with those interactions. So when two surfaces touch, they become mutually tangent, and they're said to be in contact. So physically, surfaces that are in contact can't penetrate or pass through one another. They can transmit compressive forces, and if there's friction, they'll transmit tangential forces as well. So parts that are in contact don't transmit tensile forces. So surfaces are normally free to separate or move away from one another if they're not glued or welded together. Okay, so contact is classed as what we call a changing status non-linearity. So the stiffness of the entire system depends on the contact status. So whether the parts are touching or separated, or if parts are partially touching, and then less area is in contact as the load is applied, that is essentially a changing status. Okay, so in contact, there's basically 5 different types of contact, and we'll cover these in a fair bit of detail. So there's bonded, no separation, frictionless, frictional, and rough. So the ones in italic are non-linear contacts or changing status contacts. So the other 2, bonded and no separation, are classed as linear contacts. Okay, so if we look at the situation when we've got the pin in this hole, so depending on whether it's welded or glued, or whether it's just a transition fit, there's a different contact that's appropriate for representing the behaviour. So with a bonded contact, as we pull up on the pin, the bottom, let me just grab a pen. The bottom part here of the hole follows the pin. So with no separation contact, the same thing happens, but around the sides, you can see that it's hard to see, but there's a bit of sliding going on. Okay, so with a frictionless contact, so here the displacement is exaggerated. You can see there's a gap opening up here. Okay, so the same thing with frictional contact, and the same with rough. So because these are all non-linear contacts, they don't support a negative pressure within the contact. Okay, so with frictionless, there's a lot of sliding going on around the pin as well. So with frictional, whether it slides or not will depend on whether it's overcome the static friction. With rough, there's basically an infinite friction coefficient. Okay, so when we look at contact results, so particularly for non-linear contacts, so there's a state or status of the contact. So it tells you what parts or what area of your part is in contact, and also what the interaction is, whether it's close to being in contact or whether it's far away, and also whether it's sticking or sliding. Okay, so because with the contact, so just exaggerate the gap. So there's the state in this normal direction, and then there's also the state in the tangential or sliding direction. Okay, so if you need to know, particularly for a frictional contact, what the states are in both the tangential and the normal direction. Okay, so when parts are in contact, the amount of load or pressure between them is important. So the contact pressure tells us how hard the surfaces are being pressed together. So we can look at this as either a so if this is basic, so that's essentially a force. So that's essentially a pressure, and in the tangential direction, that's essentially a shear pressure or a shear stress. Okay, so again, if there's sliding, then you'll get a frictional shear stress. So that shear stress will also be there with a rough contact, because there's essentially no slip. So that means that there'll be a stress developing. So you can also plot this pressure for a bonded contact and for a no separation contact. So we'll explain why or where that can become important in a few slides. Okay, so with the contact states, so here for sticking, so that means in the shear directions, there's no relative movement. So with sliding, so that means in the normal direction we're closed, but in the shear direction we're essentially open, or there's movement. So when we're in near contact, it means that there's a gap between the parts, and they're not in contact. Okay, so with a far contact, it means we're outside the pinball region. So there's this other state that we sometimes see, which is over-constrained. So we see this when you've got an MPC contact applied to a face with a support condition, or if you've got two MPC contacts on the same face. Okay, so here we, if we look at the contact status for different contact types, we can see we've got a contour plot, which there's basically 1, 2, 3, 4, 5 different colours. So with a bonded contact, it's essentially sticking. So that means there's no sliding and there's no gap in the normal direction. So it's closed in the normal direction, closed in the sliding direction. So with no separation, it's basically a so that these are, if you probe these, they've got different numbers. So 1 is sticking, 2 is sliding, 3 is near, and 4 is far. So here we're basically sliding. Sorry, that's the other way around. I think 1 is near, 2 is sticking, and 2 is sliding, and 3 is sticking. Okay, so so here we're closed in the normal direction, but we're free in the tangential direction. So that's why it's sliding. So with the frictionless contact, where there's a gap, it will have a near contact status, and because it's frictionless, wherever it's touching, it's sliding, because it's sliding because there's no frictional resistance. So with a frictional contact, we've got a friction coefficient. Up the top here, it's basically, it can't slide, and it's basically closed and touching. So on the sides, it's because the normal force is quite low. It's able to slide, and then on the bottom, it's open where we've got a gap. So with a rough contact, so at the top where it's touching, because we've essentially got an infinite friction coefficient, the parts can't slide relative to one another, so it's in the sticking condition. And then it transitions to a near contact where we've got the gap. Okay, so if we also look at the contact pressure, so remember this thing is being pulled up. So you can see here we've got regions of negative contact pressure, sort of around here. So this is only possible if these parts are welded or glued together. So if this was just a press fit, a negative pressure isn't realistic. It's not physically meaningful. So especially when it's spread over a large area. So where you've got negative contact to separate. So by having a bonded contact there, you're stopping that from happening. So effectively, although you solves, it's not the correct result. Okay, so with a no separation contact, so again we get a high negative pressure, but you can see the peak pressure is higher. So they're still trying to pull away from each other. So it's again indicating where they're trying to separate. Okay, so with a frictionless contact, so you can see that there's no negative in the scale. So essentially, where you have a zero pressure, the parts separate. And then where the pressures are positive, that's where the pin is being pressed into the hole. So it's capturing that that behaviour. So the pressure variation across the top. So you can see that it's higher at the sides, and it's lower in the middle because the pin is bending. Okay, so with a frictional contact, you can see there's a little patch in the middle here where it's actually 0. So the contact is open. So because the pin is bending, so it's allowing that part there to separate off. Okay, so so with rough contact, so there's this little patch here. So because the housing is bending, it's sort of causing that to come into contact, and then there's a band of negative pressure in the middle. Okay, so so the gap, so the arc is smaller. The gap in the arc is smaller than the previous two cases. Okay, so when we have parts in contact, so probably the most general case is a frictional contact. So the real condition lies somewhere between frictionless and rough. So with a friction coefficient somewhere between 0 and infinity. So in reality, the friction coefficient will be somewhere between 0 and 1. Okay, so so if you've got sliding behaviour, so there may or may not be significant frictional effects. So when that's the case, you can use a frictionless contact. But the main thing you've got to remember is that when you've got sliding or relative sliding, there's no resistance. So that can cause issues like rigid body motion, and the model will fail to solve. So with frictional contact, so when you do have your parts starting to slide relative to one another, there'll be a shear force or a shear resistance that develops between the two bodies. Okay, so frictional contact is supported for both small deflection and large deflection, although usually it's large deflection. It's not very often used with small deflection. So when we have friction, there's a lot of different things that come into play that determine the friction coefficient. So the different materials that are in contact, if there's a lubricant in between, the surface roughness, the temperature, the relative velocity of the bodies, and other attributes as well. So we can approximate these different things mathematically just with a single value, which is the friction coefficient. So that basically captures all of these effects. Okay, so there's simple tests we can do to determine the friction coefficient between two bodies. So common thing that's done, you have the two parts. You slowly raise this or pivot this surface, and then when the block starts to slide, that's when you can calculate the friction coefficient based off the sine of the angle of this plate here. Okay, so if you look at a force displacement relationship, so the force builds up. So this would be elastic deformation, and then in this region here, that's basically when the part is sliding. Okay, so that's essentially what we aim to simulate. So mathematically, we basically use Coulomb's law. So the tangential force has to be less than or equal to the friction coefficient times the normal force. So once that is exceeded, then the part will start sliding. Okay, so here this is the coefficient of static friction. So by default, the kinetic friction, or the friction coefficient between the two moving bodies, is the same. So for some materials, that's not the case. It is possible to model that in Ansys. It's just not exposed in the user interface. Okay, so if we do a graph of this, so it's basically a straight line with the gradient being the friction coefficient. Okay, so if we convert this into a stress, okay, so this is the shear direction, this is the normal direction. Okay, so there'll be a certain limit based on the interaction between these two surfaces. So if you think of this as basically an elastic plastic material, once you start shearing the material, then you'll get sliding as well. So this is essentially a shear stress limit. So it's normally so it's normally 0.6 times the yield stress. So you can put that in as a limit, and one of the workshops I'll do will actually show the effect of that shear stress limit and how it can affect your result. Okay, so here we've got an example of, oops, sorry. See if I can get that animation to play on here. Okay, so here this is an example of basically frictional contact with a large amount of relative sliding. Okay, so you can see the part sort of slides and passes through the gap. Okay, so here we haven't set a shear stress limit. It's just been able to overcome the shear stress just based off the normal force times the friction coefficient. So here in this example, so this is basically a section of a wiper blade. So you can see it's sort of jumping. So that's because it's sort of sticking for a little while and then letting go, sticking and then letting go. So when you've got your wipers on and you hear them screeching, that's basically the rubber sort of flapping backwards and forwards. So there's different things you can do to alleviate that. So if you put a little bit of soap in the windshield washer bottle, it acts as a lubricant. So there's also treatments you can put on the glass, although they will wear off very quickly. Or when you put on new wiper blades, there's still oils from the manufacturing process of the rubber. So they also act as a lubricant. Okay, so we'll talk now more about the mathematics of contact. So how contact is handled by the solver. So there's different ways that this is achieved. So we call this sort of contact compatibility. So when one part can't pass through another, contact compatibility is enforced. Okay, so that's essentially when we prevent penetration. So there's different what we call contact formulations that are used to enforce the compatibility at the contact interface. Okay, so you can see here we're applying a force. We've got one side is the contact, one side is the target. So the contact shouldn't be able to pass through the target. So these red and blue elements are basically a skin overlaying your solids. So that's mathematically how we get the parts to interact with one another. Okay, so the first type is what we call the pure penalty formulation. So here this essentially relies on a small amount of what we call penetration. So this is the penetration here. So that small amount of penetration is coupled with an artificial spring. So the penetration times the contact stiffness gives us this normal force. Okay, so this is an artificial force that's introduced to enforce the contact compatibility. So ideally we want this penetration to be close to zero. So that implies that this stiffness is close to infinity. Okay, so that means that this force here is going to be quite high. Okay, so if that force is too high, so if this was on the end of a cantilever, it's essentially going to force that or push that part out of contact. Okay, so that's not ideal. So we essentially allow a small amount of penetration to enforce the contact compatibility. So we can fine-tune this this normal stiffness, because this isn't something you can physically go and measure. Okay, it's going to be different for different situations. If you change the mesh density, the ideal value for the normal stiffness will change. So if you have different materials, then it will have a different different value. Okay, so the more accurate result is to have your penetration as small as possible. So you just want it to be something realistic. So if you've got a 100mm shaft, you might allow, say, a 0.1mm penetration. So 1mm of penetration might be too big. So you can do sensitivity studies to reduce the penetration to the point of the model not converging, and that's essentially your sweet spot, where your normal stiffness choice is giving you a numerical result as well as a physically meaningful result. Okay, so another formulation is what we call the normal Lagrange formulation. So here we add an additional degree of freedom, the contact pressure, to satisfy contact compatibility. So this force we're applying, so to get a reaction force from the contact, so this is basically the pressure times the area in contact. So the area in contact will sort of come to an equilibrium point, and then the contact pressure that we calculate. So here we have pretty much zero penetration because we're calculating the pressure degree of freedom. So you don't have to have a contact stiffness. So that means that there's no sort of relative slip in the normal direction. So the downside is with this is it requires the direct solver, and this is more computationally expensive. Okay, so this only applies in the normal direction. So in a sliding direction, you've got a similar thing. You have to have a small amount of relative sliding to transmit shear forces. Okay, so another contact formulation is what we call the Augmented Lagrange method. So here, this is basically the penalty method. Just do it as PM for short. And then here, this is an additional term we add. So it's basically an additional force that's there to reduce the penetration. Okay, so because of this additional term here, the Augmented Lagrange method is less sensitive to the magnitude of the contact stiffness. Okay, so you generally wind up with less penetration for a given contact stiffness. So this Augmented Lagrange method is the default method that's used whenever we have program controlled in our contact. Okay, so another method, so this is used for linear contact, so for bonded and no separation. So here we essentially tie the degrees of freedom together with constraint equations. So as the red surface moves up, the nodes that are tied on the blue surface will follow. Okay, so you can have large deformation effects supported with MPC contact, and again, it's only for bonded and no separation type contacts. Okay, so another important aspect of the contact is where we detect the if contact is happening or not. So pure penalty and Augmented Lagrange by default use Gauss point detection. So if we look on the surface of the element, we have these points internally called the Gauss points or integration points. So they'll have a position in space in the depth of the screen. So when they try to cross a nodal segment on the target, that's when contact is detected. So with nodal detection, so you directly use the nodes on the contact elements. They try to cross a target segment. That's when contact is detected. So Gauss point detection has difficulty dealing with sharp corners because your Gauss points would be somewhere in here. If that's your nodal segment, contact isn't detected until that point there. So you'll have a small amount of artificial penetration that's not accounted for. So if you've got lots of sharp corners, you sometimes need to change your detection to nodal detection. Okay, so the other important thing is for contact, particularly for non-linear contacts, is the normal stiffness factor. Okay, so this is essentially a scale factor of what's calculated by the solver. So by default, 10 is used for bonded and no separation, and 1 is used for all the other contacts. So when you have so there's a few situations where you would change this. So because this normal stiffness factor is loosely based off the Young's modulus of the materials. So if you've got something like, let's say, a rubber block and you're pushing a steel sphere down into it. So because so this is of the order of, say, 2E9, and this rubber here is of the order of say 10. So 10E6. So there's quite a difference in the Young's modulus of these two materials. So it usually takes the average of these two materials and then it uses a scale factor. So because the average is, well, a lot closer to 2E9 than to 10E6, we need to lower this this stiffness factor, so that then the contact stiffness value is closer to the Young's modulus of the material. So another situation, so here it says bending dominated. Well, what does bending dominated mean? So it's normally when you got a very flimsy part in contact with a very stiff part. So this is a steel material. So I'm pushing this up against a ramp, or pushing the ramp into this flimsy arm. So remember, we've got the contact force being developed because of the presence of the contact. So remember, that force is artificial. So if that force is quite large, it can bend the arm out of the way. So then in the next equilibrium iteration, there's a force present at the bottom here because of the contact. That's enough to overcome or to deflect the arm upwards. In the next equilibrium iteration, that force disappears. The arm is got some internal energy, or it's got it's essentially like a spring that's been held back. There's no force causing that deflection, so it suddenly springs back or tries to go into contact, and you get this this oscillation. Excuse me, this oscillation going on where it never comes into contact. So you use a lower value for the contact stiffness, and then the contact will eventually establish itself. Okay, so another thing we can do is we can adjust the contact stiffness. So the solver can adjust it based on how the model is solving, if it's having convergence difficulties. So so by default, the update stiffness will occur at each iteration. So you can use this each iteration aggressive. So you can, so if you think of this as your contact stiffness factor, so it might sort of go from 1 to, say, 10. No, let's go the other way. Okay, so it might start off at, let's say, 1. It finds that there's difficulty in convergence, so it ramps it down to maybe 0.1. Okay, so then it might sort of stay steady for the rest of the solution, but it can adjust this sort of up and down based on convergence. So remember that if you lower the contact stiffness, you're going to get more penetration, and that may be mathematically valid, but it might not be physically valid in terms of being realistic in terms of a real solution. Okay, so here in this example, we can show the effect of contact stiffness. So this is basically a quarter symmetry model of an interference fit. So this part is larger than the other. So the aim is we want to resolve that interference. So if we look at the changing or increasing the normal stiffness, augmented Lagrange is the baseline case because that has no penetration. So if we look at the maximum deformation, that doesn't change very much. If you look at the equivalent stress, it also doesn't change very much. But if we look at the contact pressure, you can see that it's 0.979, then it jumps up, and then it jumps up again. So between 1 and 10, there's not much change. But if we look at the iterations, you can see that that's changing. That's basically getting harder to solve with the higher contact stiffness. And also, if we look at the maximum penetration, that's coming down as we increase the normal stiffness. But depending on the size of this ring, we could then decide on what's an acceptable amount of penetration. But in interference fit problems, probably the important thing to look at is the contact pressure. When that starts to stop changing with increasing your contact stiffness, then that's when you've got the correct both mathematical and giving a realistic solution value. Okay, so very important concept for contact is what we call the pinball region. So when we had the contact states with sticking, sliding, near and far. Okay, so if we look here, so here where it's touching, so this is sticking. So depending on whether it's frictionless or frictional, it could be could be sliding as well. Okay, so anywhere where we've got a gap and it's in the pinball region, this is classed as what we call near contact. So this would be open. Anywhere that's outside the pinball is what we call far contact. Okay, so for non-linear contact, so if this was a wheel that was rolling, it's only looking for impending contact within the pinball region. Okay, so in the next iteration, only that node can establish a new contact. Okay, no, sorry, that's around each node point. So if this was, say, smaller, then so we drew the pinball around here. If it was only that size, then it only searches locally in that region for impending contact. Okay, so for a bonded contact, essentially anything that's inside the pinball and there's a gap will transfer load. So this is important when you've got sort of small artificial gaps in your model. But it's also important if you've got interference. Okay, so if you've got one part penetrating into another, so the has to be big enough to see that that's got a what we call a negative gap or an interference. So by default, pinball is based off the mesh size. So if you refine your mesh, you can suddenly find that your bonded contacts stop functioning. Or if you've got an interference fit, you suddenly find that your parts don't transfer load if you're ignoring the gap. If you're resolving interference, the interference doesn't get resolved. Okay, so there's always a like all things in FEA, there's a balancing act. So if your pinball regions are too big, the solver spends a lot of time searching for possible contacts. If it's too small, it may not detect contacts. So that's for non-linear contacts. So if it's a linear contact, so it determines the amount of allowable gap or penetration. And for MPC, it affects how many nodes are tied up in the MPC. Okay, so we can specify a pinball region to be a fixed value. So here it will be independent of the mesh size. Okay, so here we've specified a 2.5 millimeter radius, and this is bonded. So this is going to transfer load even though there's a gap. As long as that gap is smaller than the pinball, load will be transferred. When we refine the mesh, it'll stay at that 2.5 millimeter. The pinball will stay at 2.5 millimeters. Okay, so when we talk about contact, we've got different types of behavior. So we've got symmetric and asymmetric, and there's also auto-asymmetric. So with an asymmetric contact, the nodes on the contact can't penetrate the target surface. So this is important to remember. So on the top, the red mesh is on the contact side, and the green is the target side. So you can see there's only one element across here. So when these nodes try to cross that target segment, they can't go any further. So the contact is established. So on the right here, the red is again the contact, but it's much coarser. So you can see that the target surface is able to penetrate because these target segments are crossed by that node. So this artificial penetration that you get will obviously affect your solution. So how do you decide which to do as the contact, to do as the target? So if you do need to do that, so the following guidelines enable you to select. So some of these you can't really control. Others you do have control over. So if one surface is larger than the other, you've got control over that. So if one surface is convex and one is concave, you can't really change that aspect, so you have to choose. So if one surface is coarse, one is fine, you can you've got control over this. You can reverse these. So if one surface is stiffer than the other, you don't have control over that. So you're basically forced to choose the stiffer surface as the target. So if one surface is high order, one is low order, well, you do have control over that with the meshing. So you can get conflicts with these, but generally the probably the most important one is this one, stiffer versus softer, and also the convex and concave. There's two ones you probably encounter most. Okay, so so one of the other things that's sort of not mentioned here is auto-asymmetric. So when the contacts are set up, so these are the two bodies. So this is contact pair 1. This is contact pair 2. The solver decides which one of these to eliminate. So internally it uses some logic to decide, and most of the time it's to do with the mesh and also the stiffness. So this contact will get eliminated from the solution. So it's only this contact that's this interaction that's checked. So the contact against the target. So we don't need to check this body against that body because it's already been checked one way. Okay, so another important thing is contact surface offset. So there's different options we can use here. So we've got adjust to touch or add offset. So adjust to touch allows the solver to determine what sort of offset to apply to the contact to close the gap, so it's just touching. So the contacts need to be, the nodes need to be within the pinball for that to happen. Okay, so it's usually used for small adjustments. So you might have sort of differences in size because of the way you've modelled in CAD. So another thing we can do is we can mathematically add an offset. So this can achieve either a positive or a negative between the contact. So a positive value will tend to close a gap, and a negative value will open a gap or reduce an interference. Okay, so this add offset can be used to model interference. Okay, so we'll see that. No, I can't really show that with the model. So, so this is body 1. This is body 2. So these are axisymmetric. So there's an axis of rotational symmetry here. So this might be a say a bushing going into a machined bore. So there's this interference here. Okay, so when the solver solves, it will sort of create reduce this interference and then create internal stresses in the parts. So the way we achieve that is with, so here we've got an add offset. So the offset value is 0, and here where you can do it either with ramped effects or no ramping. So here think of this as the this is our interference. So we're basically ramping the interference out with substeps. So the reason we do that is because there'll be forces generated because of the interference. So instead of that force being step applied, it's basically ramping that force, or ramping that force down. So when we have at offset no ramping, it tries to remove the interference in the first sub-step. So that can result in quite significant convergence difficulties. Okay, so another common situation you'll come to in contact is rigid body motion, or the possibility of having rigid body motion. So here we've got a gap, and that gap is present just because of the way the model is. So we need to account for this. So when we're solving for a static analysis, so because there's no, essentially each node has to have a stiffness path to ground. So because this body is free floating, there's essentially no stiffness path to ground. So the stiffness matrix is singular, and we can't invert it. So therefore, we can't get a solution. Okay, so this body can move without restraint. Okay, so if we've got a bonded or no separation contact, we're allowed to have a gap. But if it's frictionless, frictional, or rough, we can't have an initial gap. So you can add an offset, but then that might not be what you want. Okay, so what we can introduce is what's called contact stabilization damping. So this introduces basically a force that's proportional to what we call the pseudo velocity. Okay, so with this force, this body will move a certain amount in a time step. But at the same time, we've got essentially a damper here. So because we have delta x over delta t, so that's a velocity. So that velocity times the damping gives you a force, which essentially balances the force you're trying to apply. Okay, so this contact stabilization damping will allow these two parts to come into contact. So you've essentially got rigid body motion, but it's controlled and balanced. Okay, so once the bodies are in contact, there's no relative displacement. So this force basically has a zero value. So it's just there to control the initial movement. So this can be in the sliding and the normal direction, but it's most commonly encountered with gaps in the normal direction, like a pin in an oversized hole, for example. Okay, so I'll just show this on this animation. So here we've got a gap. So the top is being pulled up. So you can see it closes the gap, and then the contact or the load is all distributed at the bottom. Okay, so here in this example, so there's two ways we can deal with this situation. The first is to do an adjust to touch, and the second is to use contact stabilization damping. Okay, so here this is looking at the normal stress in the so I think that's the y direction. So you can see we get the compressive stress sort of concentrated at the contact point. and you can see the gap is closing. So with an adjust to touch, there's this artificial gap that's present, and you can see the stress distribution is quite different here. So it's not all being concentrated just at the point where it's touching. Okay, so that's the end of that chapter. So what I might do now is go through an example. Okay, so with the contact stiffness. Okay, so bolt and concrete are bonded first, but at some point bolt debonds. Yeah, you can do debonding contact, although that's a little bit more advanced. You can do there's a traction separation law you can apply. So you can do it as either, let me see if it's possible in here. Here we go, cohesive zone. Okay, so here you can do a different properties. So you can do fracture energy based debonding, or separation distance based debonding. So there's, if you look in the help, it explains to you what parameters you need to put in, and sometimes you need to fine tune these parameters to get close to reality. Okay, so I won't worry about doing that bolt thread. Okay, so this is basically a 2D model. So when it comes up, so just modeling contact interaction. I just need to assign the material. Sorry, I'm going to need to open this project again. Okay, all right, so this is my my setup. So if we look at the contact, so it's a frictionless contact. So the contact is the upper body, the target is the lower body. So if we look at the mesh, the target side is only one element, whereas the contact is much more finely meshed, and it's convex in contact with a flat surface. Okay, so if we look at the contact settings. Okay, so with the normal stiffness, I'm going to change this to a factor. So I'm going to use 0.01 to begin with. And I'm going to turn update stiffness on to each iteration. Okay, so then we'll let it solve. Okay, so this is the force convergence. Okay, so if we look at the directional deformation, so that's the, so we look at the contact pressure. So I'm just going to insert a image there to capture the pressure and also the penetration. So pressure and penetration are basically the two things we should look at. Okay, so now I'm going to up my penetration. So normally you do it by a factor of an order of magnitude. So I'm going to do it 2 orders of magnitude just to speed things up. Okay, so if we look at the pressure, so that's, why has that gone down? It's done the reverse of what I expected. Okay, so let's Okay, so I'm just going to look at what the contact stiffness did. Okay, so it's automatically reduced it. So I could have reduced it, yes, by quite a lot. Okay. Go back here and see what the Okay, I'm not sure what's happening there, but let me change this formulation to normal Lagrange. Have to delete that because it's not valid. Okay, so that's the pressure, and the penetration is close to 0. Okay. All right, so another example is contact stabilization damping. Okay, so here if we look at this, so it tells us the radius, 12.7, 13.4. So there's quite a significant gap there. Okay, so here what we can do, so if we look at the mesh, so if I insert a contact tool, so this can tell me things. So here we can see there's a 0.79 geometric gap. Okay, so it's a asymmetric contact. So the pin is being held and there's a pressure load applied at the top. So if I try and solve this, so it's giving me an internal solution, magnitude limit exceeded. Okay, so I can go here and turn on weak springs. Okay, so I get a solution. Oops. Okay, so there's 4.2 E5 millimeters of displacement. So that's obviously not a correct result. Okay, so let me turn off weak springs, but this time in the contact. So let's do adjust to touch. Okay, you can see we've still got the gap there. And the hole is stretching. So what happens in reality is that gap closes. So in order to simulate that, so if I just change this back to what it was, so this is stabilization damping factor. So just start off with a value of 0.02. Okay, so you can see that there's been, so if I probe down here, so it's closed the gap and there's some elastic deformation as well. So if we look at the equivalent stress, we can see it's all focused around the bottom here, which is what we expect. So we've captured the rigid body movement. So if we animate that, you can see the gap closes, then the load is transferred. Okay. So this last example, I'll show you how to modify the behaviour of a frictional contact. Okay, someone's asked, can one obtain similar results if you analyse only block with the hole and add a force reaction? You could, but when you do that, you're not getting you don't know what the angle of contact is. So depending on how hard you pull down on the pin or pull up on the housing, the angle of contact is going to be different. Okay, all right. So here in this model, so I have there's a bilinear material with a 200 MPa yield strength and a 0 tangent modulus, so basically an elastic, perfect plastic material. Okay, so essentially forcing this billet down by 40 millimeters. Okay, so that's what happens. Okay, so you can see that the block is sticking to the side. Okay, so if we examine this in a bit more detail, so if I insert a contact tool, and I insert a frictional stress, because that's essentially the shear stress. So you can see it goes as high as 631 MPa. So that's obviously unrealistic, and that's why it's sticking. Okay, so what we need to do, so we need to go to the help for the contact. Okay, so there's in the contact, so there's different things for key options. And then there's real constants. So there's one here called Tor max, maximum friction stress. So I'm not sure where it says it, but basically the default limit for that friction stress is 1E20 in whatever units you're working in. Okay, so we need to modify that value. So we do this with the rmodif command. So it's rmodif nset starting location and then value. So the starting location is 9. Nset we don't know. We don't need to know it though. So here if I insert a command, so the type, the real number for asymmetric is equal to CID. So if I say rmodif, comma CID, comma 9, comma, what units am I working in? Millimeters. So if I say 200, okay, so that gives me shear stress of basically 0.6 times 200. So if I solve the model now, so now the part slides. So because it's now the shear stress that's controlling whether or not the part slides, I'm getting a more meaningful result. So if I look at the frictional stress, it's capped at 120, which is 0.6 times 200. So once it reaches that value, it essentially starts sliding. Okay, what we'll do now is we'll take a short 10-minute break, and then we'll start back at 10:40. Okay, all right, so this was the agenda. All right, so coming back to my point here, so the three things that contribute to the stiffness matrix are changing contact status, So any non-linear contacts will mean your stiffness matrix is non-linear and always changing. Change in the shape of an element. So if we go from this to this, or this to this, or even just simply a rigid body rotation of the element. So that will cause a change to the stiffness matrix. And then this last one here, change in material modulus or metal plasticity. So this really relates to the strain. So if we look at the strain at yield of a 200 MPa material, so we work in megapascals, so 200 E3. So that gives us quite a small strain. So it's a 0 point. Sorry, 1 second. .01. Okay, so this is considered a small strain. So when you have, say, at ultimate tensile strength or strain at break, we might be looking at, say, 10 to 12%. So I mean, it will depend on the material, but that's typically the sorts of values that we're getting. So if you look at something like a rubber, so you might have something that starts like this, and you can stretch it to something like that. So this might be, say, 300%. And then when you let go of the load, it springs back to its original shape. So although that's linear behaviour, it's not considered small strain. So that is also considered a non-linearity, large strain. Okay, so the stiffness matrix is built off the material moduli and the geometry. So as the geometry or coordinates change, so does the K matrix. So at each iteration, a new stiffness matrix is made based off the previous iteration's deflections or change in material states. So you have to have, what you're aiming to have is not too large a change in the geometry, so that the change in the stiffness matrix isn't abrupt. So because I mean, in a general case, you've got a curve. So you're trying to break this down into piecewise linear segments. So that's what we do when we do our sort of sub-stepping or our equilibrium iterations. We're trying to approximate that curve with straight line segments. Okay, so with contact, so at each iteration there's a new guess made for the location of the new contacts. So that will introduce additional, if you like, additional springs or additional terms to this stiffness matrix, or it will adjust the stiffness of the terms. Okay, so with material, so specifically when we're talking about metal plasticity, so we're talking about this, the effective modulus. So in the elastic range, it's the Young's modulus. In the plastic range, it's what we call the tangent modulus. Okay, so how does mechanical solve for this changing stiffness? So So you can't directly predict the response with one set of linear equations. Okay, so we use what's called an iterative series of linear approximations. So this is called the Newton-Raphson method, and each iteration is called an equilibrium iteration. Sorry, 1 second. Hello? Hello? Yes. Hello? 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 Yes, you there? Sorry about that. Okay, so there's my. Okay, so essentially this red line is our first guess at the stiffness matrix. So based off that, of an applied load, we get a displacement. So with that new displacement, we have a new stiffness matrix. So we keep repeating this procedure until we, sorry, so this thing here is the out of balance. So based off that deformed state, we can calculate internally generated forces. So we keep repeating this procedure until these two, until the applied load balances the internally generated loads. So that will come when we have a certain deformed configuration. Okay, so this dotted line we don't sort of know beforehand. Okay, so we keep doing this linear series of approximations. So you generally don't want this these lines to change too much between iterations. So what you tend to do is you tend to try and apply a smaller load so that the curvature of this line isn't too great, or it can be represented with fewer corrections. Okay, so this difference between the externally applied loads and the internally generated loads is called the residual. So this will never ever be zero because of computer precision. So we say that the solution is in equilibrium when that's within a an acceptable tolerance. Okay, so we'll talk about material nonlinearity. So particularly metal plasticity. So you might want to predict permanent deformation after an overload event, or sometimes you might want to be simulating a metal forming operation. So sometimes it's enough just to do a linear elastic material model, so we know what our yield stress is. So if you calculate stresses above yield, and if yield is considered your failure point, well, then you know that your model has, well, your loads are too great, and your structure will fail. But other times you might want to know, so this is your plastic region, you might want to know, well, what happens after I remove my load? how much load can I apply till it actually breaks. So here you'll know your ultimate stress. So you look at the stresses and calculate. Whereas if you do a linear elastic and then so your ultimate stress, would be here. But in reality, that's not how the stress strain curve behaves. It goes along here to achieve the ultimate stress. So these two are meant to be in line. Okay, so there are sorts of situations where you might want to look at modelling plasticity. Okay, so what is plasticity? So when a material experiences stress beyond its elastic limit, it undergoes yielding. So and you have permanent plastic deformations. So the strains can be quite large compared to the elastic stresses in the plastic region. So as I sort of briefly mentioned before, so here this is typically about 0.1 or 0.2%. And then here in the plastic range, this can be in tens of percent. So there's quite a large difference in the strains. Okay, so when you basically, the definition of plasticity is when you remove the load, you have permanent deformation. If you're in the elastic range, you don't get any permanent deformation. Okay, so so plasticity is important in some structures. So it's used for absorbing energy. So a lot of modern cars today have some sort of energy absorbing crash structure on the front, so that as long as the crash isn't severe, they just unbolt the crash structure at the front and then bolt on a new one with little need for repair. So that can be an example of where it's useful. Or a lot of power poles that you see on the street, or they call it road hardware. So that's designed to plastically deform to absorb energy when something crashes into it. So that's another example. Okay, so materials that fail with little plastic deformation. So these are said to be brittle, and things that have a lot of plastic deformation or ductile response, they're basically ductile. So they have a lot more deformation in the plastic region before failure, whereas something that's brittle might fail not too far after yield. So cast iron, for example, is something that's brittle, whereas a lot of aluminium alloys tend to be very ductile. Okay, so so when we're putting in plastic or non-linear material properties, we have to use what's called true stress and true strain. So when you have a tensile test, so a typical graph will look something like this. So what does this graph say? So this is our stress and this is our strain. So if you look at this another way, it's basically force divided by area and change in length over initial length. Okay, so the reason why we get a negative slope on a stress strain curve is because when you get necking occurring in a tensile test, so the real stress is occurring here, but we're calculating the stress based off this area. So when you get necking, So you still have to apply, so the force you're applying is not so much dropping off, but you're calculating it based off the initial area. So it's decreasing, whereas in actual fact, it's probably starting to taper off. So when we use true stress, true strain, we basically apply a correction. So when you have plasticity, Poisson's ratio is equal to 0.5. So essentially, if you have a bar of material, so as you stretch it, you can very easily calculate the change in area before necking. So the change in length we're measuring, so we can effectively calculate the change in area. So I won't go through all the mathematics, but it pops out that this is how you calculate the true strain. So it's natural log of 1 plus engineering strain, and for true stress, it's engineering stress times 1 plus engineering strain. So when you make that correction to this stress strain curve, you don't get this negative slope. So essentially, this is saying that to keep increasing the deformation, you have to decrease the force. That doesn't really make sense. Whereas here, when it's always going up, to increase the deformation, you have to increase the force, which makes more sense. Okay, so I've got a question about how do we get the static and dynamic coefficient of friction for different material in dynamic simulation. So probably from the literature you can find static and dynamic friction coefficients. So we can just import a scale factor between the two. So there is more elaborate things you can do, like you can change the friction coefficient based on sliding distance, for example, but that's sort of more advanced. There is some material in the help that will sort of show you how to do that. Okay, so how do we define metal plasticity in Ansys? So there's essentially two different types of stress strain curve representations that we can do. So the first is a bilinear material property. So this assumes a linear relationship between the plastic strain and the post yield stress. So you essentially put in your yield stress and your tangent modulus. So the second approach we can use is what's called multilinear plasticity. So here, if your behaviour is non-linear in the plastic region, where it's not with just one single slope, you represent it with a series of linear slopes. Okay, so these, for a strain hardening material, these will basically decrease until they become zero. So depending on the data you have, it will drive on which property you apply. So if you're going to be doing cyclic loading, it might be more appropriate to use a multilinear. But again, it also depends on the data you have. So to do a multilinear, you probably need a tensile test data. To do bilinear, all you need is the yield point, the ultimate point, and also the strain at break, or the ultimate strain. Okay, so if we look at the different, what we call different hardening rules. So here, this is a principal. These are the principal stress axes. So essentially, if you draw a stress state on these three axes, So looking down, so you have a cylinder whose radius is equal to the yield stress. So your stress state can exist anywhere inside the cylinder, and then once you're yielding, your stress state can be anywhere on this cylinder. So if this is in 3D space, so this is basically 1, 1, 1 vector in sigma 1, sigma 2, sigma 3. And then your stress state can exist anywhere on this cylinder, depending on the ratios of your sigma 1, sigma 2, sigma 3. So with kinematic hardening, the diameter of this circle stays the same. So that means that a difference in yield in tension and compression is equal to 2 times the initial yield stress. So if your strain is large enough, so when you basically unload, so this difference here is 2 times sigma yield, you can actually get yielding in compression. So that isn't physically possible. So mathematically it is, but physically it's not. So kinematic hardening is typically used for small strain cyclic loading. So with isotropic hardening, so when you yield in tension, your new yield stress in compression is 2 times the new yield stress. So you're always maintaining 2 times the current yield stress between tension and compression. Okay, so usually you don't apply this for cyclic loading, because you're just going to sort of keep increasing this this loop. Okay, so with cyclic loading, particularly large strain cyclic loading, we have a material model called the Chebauche material model. So here you can see the stress strain results, and you can sort of see a hysteresis loop developing. So with kinematic hardening, you sort of go around the loop. So you don't accumulate any plastic strain on cyclic loading, which goes into the plastic region. So this is often encountered in the turbine industry, particularly in the power generation industry. They can have what's called ratcheting and shakedown, where you get accumulations of plastic strain, and eventually the parts are taken out of service before they rupture. Okay, so here this is an example of the most basic material properties you can get. So you look on MapWeb, you find a particular grade of material. So here in particular, this is a I think this was a 250 grade material. So you got different ranges of yield stress. So this is the proof strength. So this is at 0.2% and at 1% strain. And then you've got your tensile strength. So with steels, they don't display a definite yield point. So there's sometimes this dip and then it goes into the plastic range. So in Ansys, we basically consider these 2 points to be the same. So we just have a straight transition. Okay, so and then we've got the percent elongation. So we treat these as though they're engineering stress. That's generally what they are. So if we want to construct a material property curve, so we take our engineering stress, convert them to true stress. So you can see how these are hardly any different. And then we've got our engineering strain and our true strain. And then for the yield point, you can see there's quite a difference in the engineering and true stress. And then engineering strain and true strain, so there's quite a difference there. So this strain here will contain an elastic portion. So you can see that's very, very small compared to the overall strain. Okay, so we basically take the difference in stress divided by the plastic strain, or change in strain. So we assume that the elastic portion is negligible, and then we come up with a tangent modulus. So when we input the data, so this isn't the same. It's not the same data there, but you put in your yield strength in megapascals and your tangent modulus in megapascals. So just be very careful when you're entering this data that you check the units you're entering it in. Common mistake people make is they enter it thinking it's in megapascals when it's actually in pascals. So they wind up with a yield stress of, say, 200 pascals, which means your material goes into the plastic range pretty much straight away. Okay, so so when you enter the bilinear curve, it shows you two slopes. So it shows you your elastic slope. So I'll call this E elastic, and then it shows the tangent modulus. So you should always be able to see two slopes when you're entering a bilinear curve. If you don't, you've done something wrong. Okay, so so again, that's just highlighting that there. Just make sure you enter it in the correct unit system. So try not to use a zero slope. So when I say that, I mean a tangent modulus of 0. So always use a very, very shallow slope to represent elastic perfect plastic behavior, because mathematically you're saying for one stress, there's an infinite number of possible strains your model can have. So that means that for a very, very small change in force, there's a very, very large change in displacement. So there's essentially no stiffness in the plastic region. Okay, so with those two data points that we had, so this one and this one, we can construct a what's called a Ramberg-Osgood relationship. So there's no reason why you can't represent this on a log-log curve. So you get a straight line. So the gradient of that line becomes the power, a power law relationship. So you can then convert this into a multilinear curve. It's probably going a bit overboard, but who's to say that's not how the material behaves based off those two data points. Okay, so yeah, so you can convert your tensile test data to a true stress, true strain in log-log coordinates, do a least squares fit of the plastic data. So when I say that, I mean you have, if these are your data points in log-log space, you do a linear fit to it, that's your power in your curve, and then you can do that as your sort of relationship. Okay, so when you're entering data for multilinear, very, very important that your first data point is 0. This is plastic strain, not total strain, and it's true strain, not engineering strain. And same thing with the stress. This is true stress. So you can have temperature dependent plasticity as well. So you can sort of have multiple material, multiple temperature points, and multiple data curves for those values. But the important thing to note here with the graph, this just shows the plastic strain, doesn't show your elastic slope. So the strain is obviously unitless, but your stress has to be in the correct units. Otherwise, you wind up with the same thing. You've got a material that goes straight into plasticity. Okay, so with the multilinear data, so it's basically a piecewise curve fit of test data. So it's essentially like a bilinear, but with multiple tangent modulus values, and the data pairs define the tangent modulus. So because we're talking about strain hardening, the slopes should decrease. Okay, if they increase, that's a strain softening material, and you don't usually encounter that with metals. Okay, so don't specify too many point data pairs, because you can wind up with a discontinuity in the slopes where it sort of goes like that. Okay, so you just need enough points to capture the curvature of your real property curve. Okay, so so when we enter the data, so you begin with a base material. So this sets your Young's modulus. So you then choose bilinear or multilinear. So you choose whether it's kinematic or isotropic, and then you enter the appropriate properties. Okay, so the multilinear curve just displays the post-yield behaviour in the graph. So you can create your own materials here. So and you can do curve fit of your data. So you do that outside of Workbench. So you do that in say Excel. Okay, so so with rubber materials, so as I mentioned before, so they can undergo 200 to 300% strain, and that's entirely reversible and recoverable. So engineering strain is inaccurate at these levels. So it's only really accurate up to 1%. So if we look at the difference between how engineering strain and true strain are calculated, so if we take a bar, so if we sort of stretch it in 3 steps. Okay, so here initially this is our initial length. Sorry, so our initial strain is delta L over Li. And if for our second one, we use the same incremental change in length. So this is Li plus delta L. And then for our third one, it's basically delta L over Li plus 2 delta L. Okay, so if we this is sort of calculating it incrementally. So if you do it as engineering, it will be 2 delta L over Li. And this one is 3 delta L over Li. So this is basically engineering, and this is basically incremental strain. Okay, so if you do this as a true strain, it's basically natural log of, what is it, delta L. I think that's the relationship. So, so for very, very large strains, this approach doesn't give you the correct strain. Okay, so when we have a model with plasticity or large strain, we always need to solve it incrementally. So because we're incrementally calculating the strain, you need to basically capture that with solve points. So the loading has to be gradual. So you don't want to go put a load and then have it go straight into plasticity, because it will struggle to converge. So if you've got a multilinear curve, the solution you get will be dependent on the substep size, because you're sort of jumping from one point to another. And if you do a large jump, then your strain history will not be captured accurately. Okay, so whenever you've got material plasticity, it's always a good idea to first model with a perfect elastic stress. So then you apply your force, you know what sort of stress levels you're getting. So you might wind up here in the end. So you know that when you're first loading, you want to sort of be down in this region here. So the solver will automatically substep, but sometimes you might need to go smaller than that substepping. Okay, so it helps you to sort of set your first initial substep. Okay, so if you're trying to determine permanent deformation, so if you're loading then unloading, so you'd be sort of going here and then unloading, you need to use multiple load steps. So your load would sort of do this, where it reaches a peak and then it is removed. And then you want to see the final state of stress and deformation. Okay, so that's that. Okay, so someone is asking 200%. I'm assuming that's referring to strains for rubbers. Yes, that is the case. So if you stretch a rubber band, you can easily stretch it to twice its length. Okay, so someone else is asking about failure criteria such as more Coulomb. Yeah, it's not something that I was planning to discuss, but I can show where you enter those properties. Okay, so I'll also show how we do metal plasticity as well. Okay, so in the engineering data, okay, so under geomechanical models, so we've got more Coulomb. So these are for sort of soils and sort of civil applications. So with more Coulomb, so if I double click that, you put in the coefficients to enable this this behaviour. So it doesn't generally apply to metals. at least in my experience. So that's how you would enter it. Okay, so if we look now at this this model, so I'm first going to do it as an elastic analysis, and then I'm going to introduce metal plasticity. Okay, so at the moment we've got structural steel for everything. So this is basically an axisymmetric model. So if I turn on, so it's essentially what it is, just a conical spring pressed between between two plates. Okay, so it's loaded, then unloaded. Okay, so if let's try and do a force displacement relationship. Not display time. Okay, so it's hard to see, but the two lines are basically overlaid. Okay, so what I'm going to do now is duplicate. I'm going to break the link between the engineering data. So I'm going to duplicate my structural steel, and I'm going to add plasticity. So I'm just going to do bilinear. Okay, so it's already set to MPa. So my yield strength, I'm going to make 250. My tangent modulus, I'll just make 50. So it's basically 5 times the yield strength. So when you don't have any material data, for most metals, a good approximation is somewhere between 5 and 10 times the yield strength for the tangent modulus. Okay, so I need to refresh here. So we just go back here and look at the equivalent stress. So the maximum stress is 2000 MPa. So that's way higher than any metal will go. So you'll get yielding before that point. So this is an unrealistic solution. Okay, so if I go to my spring, I've got to change that material. So that's now got a non-linear material property. Okay, so large deflection is already on. So I just want to check my sub-stepping. All right, so with my initial sub-steps, I want to make this, let's say, so what were we, 2000 MPa. So we need at least a tenth. So I'd say 20 initial sub-steps and say 5 minimum, and I'll make this 40. So if it struggles to converge, it can bisect. Okay, so oops, that needs to, no, sorry, that can be 1. So we're not actually doing anything in the first sub-step, first load step. So in the second load step, any okay, and then in the third load step, I'll just leave it as program controlled. So as we're solving, we can look at the time increment. So you can see it's increased the time increment. So if we look at the time, so this has essentially got to go to 3. So as there's bigger differences, that's when the time step is increasing. Okay, so if we look at the deformation, you can see as we move up, the spring doesn't follow because it's permanently deformed. So if we look at the equivalent stress, okay, so you can see there's some residual stress being left over. So if we look at the plastic strain, so that plastic strain will stay because it's basically permanent deformation. If we look at the elastic strain, so there's some sort of, because of the permanent deformation, there's some elastic strain locked up in there. So if we look at the force reaction, so you can see, so that's the, where are we? Yeah, so that's the load unload curve. So you can see it's non-linear when it's unloading. That's because of the permanent deformation. Okay, so sorry, there's another result I wanted to show. So let me just turn off the symmetry expansion. Okay, so what this NLSRAT value shows. So we just show the elements. So this shows the stress ratio. So if it's 1, it's yielding. If it's 0, it's the element's not yielding. Okay, so if we look at the equivalent stress, okay, so you can see that stress makes sense. So I'll just show you what can happen is if your mesh is too coarse and you're dealing with plasticity. Okay, so if I probe, so at that point there, so let's see if we've got plastic strain there, how we do. Okay. All right, so I need to go up on my mesh size. Okay, not too sure what's happened there. Let me find somewhere with a lot of white space. Okay. Oh no, this doesn't look good. Okay, if I so when you have plasticity, metal plasticity, so at each one of these plus signs are the integration points. Okay, so we calculate the stresses at the integration points, and then if it's an elastic stress state, the stresses are extrapolated to the nodes. So here you'll have 4 values of stress. And the stress value that's displayed is an average. It's an average stress. So if you have a mixture of stress states, so here if this one is plastic, so when it's a plastic stress state, it's copied to the integration point. Okay, so these are all elastic. And because we're dealing with a spatial extrapolation, it's distance-based. So if this is our stress strain curve, just drawing an elastic extension. So this is the integration point stress. But when we extrapolate, we get a stress somewhere up here. So let's say that all three of these elastic stress states were this value, and the plastic stress is here. So our average stress is going to be sitting somewhere here. Okay, so when we look at the, and if we look at our stress strain curve, for that stress, it says we should have a plastic strain of, I don't know, let's say 20%. But when we look at the plastic strain plot, it's only over here, and it's displaying something like 2%. So you start asking the question, well, what's going wrong? So remember this extrapolation, so it's based off distance. So the only way to move these integration points closer to that point there is to use a smaller mesh. So in that way, your extrapolation distance is reduced. So where you have a very sharp transition to plasticity, so where this becomes even more pronounced is if all of these stress states are elastic and they're all close to yield, so that the elastic stress it extrapolates to, all of them are above yield. So that means that your average is going to be greater than yield. So if you've got a stress that's greater than yield, your stress strain curve says that you have to have a plastic strain. But if you look at your plastic strain plot and there's no plastic strain, then that raises alarm bells. So sometimes, or a lot of the time with plasticity, the mesh density becomes important. But you won't know where you've got to refine your mesh until you've had a look at your incorrect elastic, your incorrect results that are coming from the elastic over prediction of stress. Okay, so that's why it's very important whenever you're doing a model with metal plasticity that you compare your equivalent stress to your plastic strain plot, and also use that NL-SRAT as well. So if that's showing a 0 where you've got stresses above the yield, and you've got a 0 on NL-SRAT, it means that you've got this over prediction of stress problem going on. So that's just a very important thing to check. Okay, so that was all I had to present. So if there's any questions, I'll just bring up my